All right, so before Thanksgiving, we talked about channel coding. And so for channel coding, we first introduced the basic concept of channel coding, the motivations, and how does it work. Then we talked about the two different types of error control. Okay, one is called the forward error control, and the other one is the error detection. Forward error control is actually the error correction, and for the second type is the ARQ system that we talked about, right? And then we introduced the concept of structured sequence, and we spend most of our time on linear block code. So for linear block code, it's determined by two matrices. One is the generation matrix, and the other one is the parity check.
Dr.
Yes.
Can I ask a question about?
Yeah, sure. Yes.
On our homework, we already turned it in, which on our homework is 6.8, chapter 6.8 is about linear block code, and can you show the process, like how to find it, H?
Okay. The format of the linear block code in the textbook is slightly different from. Okay. Yeah. So the structure of the linear block code in the textbook is slightly different from the one that I presented during class, but the basic idea is similar. So G is 1101, 1011, 1110, and then the identity matrix is here. That's one here, okay? So if you can write it as P times I. So to find the parity check matrix, basically what we need is we would like G times H to be 0, right? So G is P.
We just lost this. Never mind.
Okay.
My question is, what is P?
P is the submatrix here, to the left. So we divide the matrix into two submatrices. One is identity matrix, and the other one is P. Okay, and we talked about the P in our slide. So basically, G can be written as P and I. So in order for it to be 0, our H needs to be P and I, such that if we multiply these two matrices, we will have P times P plus I. No. Actually, I wrote it in the wrong way. Should be I, P, right? And basically, if we multiply these two matrices, it will be P plus P. In the binary domain, is actually 0. So our H matrix in this case is I, P, and so it will be, so that's our I, and our P matrix is 1101, 1011, and 1110. Okay, so that's the H matrix here.
I have a question about this. The identity matrix for this example was on a
right,
like on the right.
Yes.
So sometimes it can be on the left.
So the one that we introduced in our class, the identity matrix. So the only difference between this example here and the example that I introduced in class was, so the example that I introduced in class was I, P, and in this example it's P, I. So it's not going to change anything. So in our class we have H is P, I, and here H needs to be I, P. So as long as G times H gives us 0, it's a parity check matrix.
Thank you.
Any other question? Yes.
Represented the matrix in a different way.
Uh-huh.
You can present it as
Yes.
as I think horizontally, and then
Uh-huh.
to the divided check. I think it transposes.
Okay, yeah, right. So here in the slides, I'm using x times g equals to c, right? If I remember, the book is using g times x that equals to c. They're using column vectors instead of row vectors. And in my slides, I was using the row vectors. So these are just the two equivalent ways of representing the same thing. Okay. Because if we just take a transpose, that's exactly that. If we take a transpose, it's g times x. So in the book, everything is represented as a transpose of my format there.
Then I have a question then. Then how do we know which one to use?
Because for an nk code, n is always greater than k. So you look at the matrix G, if it's a wide matrix, then it's my notation. If it's a tall matrix, it's the book's notation. Right? Wide matrix means the matrix has more columns than rows. That's our notation, right? P and I, or I and P, right? So that's our notation. And if it's a tall matrix, means it has more rows than columns, right? So in that case, so we have k columns and rows. In that case, you need to put the length k vector x here to get a length n code word. So that's the book's notation, right? So you just look at the matrix G to see whether it has more rows or has more columns, and that's it. Okay? And in my notation, so we have x times G, which has k rows and n columns, and we will get a length n code word vector, right? So n is always greater than k, so you just look at the matrix. Does it have more rows or more columns? Does that answer your question?
Yes, thank you.
All right. Any other question? All right. So both of these two ways of representations are used widely in the literature. If you read some books, they are using my notation. If you read some other books, they are using a different type of notation, but the idea are the same, and the basic math are the same. Okay, it's just the notation difference. All right, so we talked about linear block code. There was a generation matrix, a priority check matrix, and then we talked briefly about the syndrome decoding. And for syndrome decoding, as long as the received information is not the actual code word, our syndrome will be non-zero. And based on the syndrome, we can figure out what is the error vector, and then we can correct the errors. But the problem is there are more error vectors than the number of syndromes, so there are lots of errors that we cannot detect. Okay, so that's the basic idea of linear block code. Also, last week I talked briefly, there are actually better decoding mechanisms. We can do soft decoding. So instead of we receive the information corrupted by noise, which are real information, okay, and they are real numbers, can take any arbitrary values. And before the syndrome decoding, we need to thresholding them to make them ones and zeros, and then we do the hard decoding. And in that case, we are throwing away a lot of useful information. And for soft decoding, we directly use the received information to do decoding, and the performance in that case is a lot better. Okay. But anyway, so that's linear block code. And finally, we moved on to talk about the basic concepts about the code, which are the error detection and the error correction capability. Okay. So basically, the design of a linear block code, the basic idea is we would like the code words to be as different as possible. If they are quite different, then it's easier for us to tell apart of two different code words, okay, even if they are corrupted by noise and errors. So we measure the difference between two code words by using the concept of Hamming distance. For Hamming distance, it's quite simple. It's defined for binary sequence. Hamming distance is simply just the number of bits that two binary sequences are different. Okay? And in the design of a linear block code, we would like the Hamming distance to be as big as possible. And when we have more than two code words in the system, we have the concept which is called the minimum Hamming distance. So the minimum Hamming distance is So we have a sequence of code words, and we can find the Hamming distance between any pair of code words. And then we find the minimum value of all those Hamming distances. And that's called the minimum Hamming distance. The minimum Hamming distance is the performance limiting factor of this code, right? So basically in the design of a code, we would like to maximize the minimum Hamming distance. And this is called the max-min design. It's a very commonly used optimization metric in reality. Sometimes it's difficult to optimize with everything. So what we do is we optimize with respect to the worst case scenario. Okay, if we can optimize, we can improve the performance of the worst case scenario, we can improve the performance of the entire system. Okay, so that's the basic idea of the max-min approach. So we would like to maximize the minimum Hamming distance. And the error detection and error correction capability are directly related to the minimum Hamming distance. Right? So if the minimum Hamming distance is d-min, then the error detection capability is equal to d-min minus 1. So for any errors, if they are less than or equal to d-min minus 1 bits are in error, then we can always detect it, right? If there are d-min bits in error, then one code word after d-min bits are in error could be a different code word, which will also be a valid code word. And in that case, we will not be able to detect that error. So if the error are d-min bits, there is a possibility that we will not be able to detect it. Okay? So therefore, our error correction detection capability is d-min minus 1. So as long as we have d-min minus 1 or less bits of error, it's guaranteed that this code will always be able to detect it. Okay? Because if there are d-min minus 1 or less bits or less number of bits in error, the result and the received code word will always not be a valid code word. And the error correction capability is all error patterns with error bits less than or equal to d-min minus 1 divided by 2, and then take the floor operation, okay, which is the integer part of this number. We take the floor operation, that's how many bits can be guaranteed to be corrected. Okay, so for example, in our example that we saw in the previous section, we found out that d-min equals to 3, so which means all 1-bit error can be corrected and all 2-bit errors can be detected. If there's a 1-bit error, it's guaranteed that we can detect it, we can correct it, right? And if there are 2 bits of error, we can detect it. So all of these actually can be generalized into algebra, and specifically in vector space. Okay, so vector space Vn can be considered as the set of all length n vectors. Okay, it's the set of all length vectors is called the vector space Vn, and a vector subspace is a subset of S of vector space Vn. Okay, and if it satisfies the following two conditions. Okay, so for all the length n vectors, and we form a set, and we call this set as a vector space. Okay, and out of this vector space, we can also find a subspace. The subspace is essentially a subset of the original set. Okay, but in order for this subset to be a subspace, it has to satisfy these two conditions. The first condition is the all zero vector needs to be in the subset, and the second, the sum of any two vectors in S is also in S. This is called the closure properties. All right. So the linear block code, the code word actually they form a subspace. Okay. So for a code word, as we recall, if we only consider the binary numbers, the code word length is n. Okay. So totally we have 2 to the power of n possibilities of the sequences, and all these 2 to the power of n sequences put together is called a vector space. Okay, this is a vector space, and then our code word is just we only have 2 to the power of k code words, so we need to pick 2 to the power of k code words out of these 2 to the power of n possible sequences. Okay, so those 2 to the power of k code words actually they form a subspace. Okay, so let's check if the conditions of a subspace is satisfied. The first condition is the all zero vector always need to be in a subspace. Okay, so based on our linear block code, so we have x times g, c equals to x times g. If our information is an all zero sequence, and then it's guaranteed that our C will be a all zero sequence, right? So which means the all zero sequence has to be a code word in the of the linear block code. So which means the all zero sequence is in S. And another condition is the summation of any two code words has to be another code word. So this can also be verified. So let's see if we have two messages, x1 and x2. Both of these two messages are length k vectors. Okay, so we are talking about vectors here. So the code word of message 1 is x1 times g, and the code word of message 2 is x2 times g. So we claim that C1 plus C2 is also a valid code word. And why? Because C1 plus C2 can be written as x1 plus x2 times g. And again, all these operations are binary operations, okay? So x1 plus x2 is still going to be a length, it's still going to be a length k binary vector. If x is a length k binary vector, then this has to be a code word, okay? So therefore, the summation of two code words is still a valid code word, okay? Another way to verify this is, so we have C1 plus C2 times h is x1 plus x2 times g times h equals to 0, right? As long as g times h equals to 0. So for any valid code word, it multiplies the parity check matrix, it needs to be 0. So C1 plus C2 is also a valid code word. So for any two code words, we add them up together, we are going to get another code word. Okay? Any question? Therefore, all the code words of a linear block code, we put them together, we get a subspace. Okay, so that's the basics of linear block code, and we need this knowledge in order to design better linear block code. All right, but we are not going to go into too much details there. All right. Question? And actually, this property here, the summation of any two code words is still a code word. It can be helpful for us to find out the minimum Hamming distance. And when we introduced the concept of minimum Hamming distance last week, I talked about to find the minimum Hamming distance actually is quite easy. We just list all the code words and find out the code word that with the least number of ones. And that code word, the weight of that code word is equal to the minimum Hamming distance. Okay? So the weight of a code word is the number of ones in a code word. Okay? That is defined as the weight of a code word. The weight of a code word is the number of ones in the code word. Okay? The number of ones in the code word. So that's the weight of the code word. So actually we can have a theorem. The minimum weight of a code word equals to the minimum Hamming distance. Okay? So C is in the subset. The minimum weight of a code word equals to the minimum Hamming distance of this linear block code. So for all the code word, we can find the weight, except 0, okay? And of course, the minimum weight is always 0. For all zero sequence, it's always 0, okay? So how do we prove this theorem? And we prove this theorem actually by using, we can prove this theorem by using the property that the code word is a linear space. Okay? So first of all, if we have two code words, if we perform C1 plus C2, and what do we get here? So if we perform the summation of two code words, C1 plus C2, and actually we will get a new code word, okay? And actually I'm gonna show first that the weight of C1 plus C2 equals to the Hamming distance between 1 and 2. Okay? So first I'm going to show this. Now why is this the case? If you consider the summation in binary domain, so if we perform summation, what will be 1? If the 2 bits are different, we will get a 1. If the 2 bits are the same, we will get a 0. So which means if we add up 2 code words together, and we look at the locations of the ones, that means the locations that those 2 code words are different. Okay? So the summation, for the summation, if the summation result is a 1, then it means those 2 bits are different. And that's why the weight of C1 plus C2 equals to their Hamming distance. Because the weight of C1 plus C2 tells us how many ones we have in C1 plus C2. And each one corresponds to 1 bit is different. Okay? So the weight tells us exactly how many bits are different between C1 and C2. So that's why weight of C1 plus C2 equals to D1, 2. And then the rest is simple, right? And the C1 plus C2 is also a code word. Okay? So C1 plus C2 is a new code word. So for any pair of C1, so for any pair of C, let's see, to generalize, weight Ci plus Cj equals to Dij. And it's going to be a code word. So for any pair of code words, their summation is always another code word there. Okay? And then therefore, the minimum of this weight equals to the minimum of the Hamming distance. Okay? And this is a valid code word. So that's a C there. So the minimum of the weight of the code equals to the minimum Hamming distance. So when we want to find the minimum Hamming distance, the straightforward way to do is actually we compare the Hamming distance of each pair of codes, right? But that takes efforts. That takes a lot of efforts. And how many pairs of code that we have? Totally we have 2 to the power of k code words, and we need to find the distance between each pair of codes. We need to calculate this many distance. And on the left-hand side, we only need to calculate 2 to the power of k code words. So the computational complexity is much, much lower. Okay? So in that case, we just list all the code word and find out the minimum Hamming distance of the non-zero code word. And that's it. Okay? Minimum weight of the non-zero code word. Any question? Right. So that's just a simple proof of my claim that I made last week. All right? And this proof will require the knowledge of the linear vector space. Okay. So as a simple example, if let's see n equals to 3, so the vector space V3 is going to be the set of all the length 3 sequences. 2, 3, we have 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Right? So that's the vector space. And we would like to find out are the following subsets of the vector space a subspace. Okay? So we just check against those 2 conditions. The first condition is 0 has to be in the subspace. Okay? So the first condition is satisfied. The second condition is the summation of any 2 code words of any 2 elements still needs to be in S. Okay? So 0, 0, 0 plus 0, 0, 1 is still 0, 0, 1. It's still in there. So the first one is a subspace. So this is a valid linear block code. Okay? For the second one, it's easy. 0 is not there. So it's not. Okay? It's not a subspace. For the third one, 0 is there. Okay? So the first condition is satisfied. So next, let's check the remaining conditions. So let me still just write on, I still need to enable editing. Okay, so for the third one, so 0 plus any element will be the element itself, so we don't need to check. So 001 plus 010 will be 011, which is in the subset, which is fine. And then 001 plus 011 is going to be 010, which is here. That's fine. And the last 010 plus 011 is going to be 001. Is here. So that's a linear block code. That's a subspace. Okay. So that's for this one. And for the last one, so 100 plus 010 is 110. 110 is not in the subset. Okay, so this is not a subspace, and this is a subspace. Okay, it's pretty straightforward. Any question? So for linear block code, it has to be a subspace. We just verified that by its definition. So for nk linear block code, so the 2 to the power of k length n code words form a vector subspace of Vn. Okay, so graphically, we can consider the collection of all these points. They are the vector space. Okay, so totally we have 2 to the power of n points. So each length n vector can be represented as a point in an n-dimensional space. Right? So we have that many points. And out of these 2 to the power of n points, we only need to pick 2 to the power of k points to be our code word. So how do we pick the 2 to the power of k points? So geometrically, we would like these 2 to the power of k points. So these big black dots are our valid code words, right? They form a subset. So when we pick these big black dots, geometrically you can imagine we would like them to be as spread out as possible. If they are spread out, then in that case, we can maximize the distance among them. If they are all congregated together, then their Hamming distance will be small, right? Geometrically, we would like them to spread out, evenly spread out over the entire vector space. And in that case, we can maximize the minimum Hamming distance. So that's the basic idea in the design of a linear block code. We would like the picked code words to be evenly spread out as much as possible in this entire space. Okay, so that's just a geometric representation. For an n-dimensional space, it's difficult to imagine, but we can easily do this in the 2-dimensional or 4-dimensional space, or 3-dimensional space, right? We can actually draw this. For example, if we are doing this in a 2-dimensional space, just to be simple. So that's 0 and 1. That's 1, 1. So the vector space in this case is 00, 01, 10, and 11, right? So in this case, these are the 4 black dots in this case, 2-dimensional. And let's see if we design a 2-1 code, right? So the code word length, the information bit is 1. So 2 to the power of 1, we have just 2 code words. So all of these 4 possibilities, we would like to pick 2 dots to be our code word. And when we pick those 2 dots, the first thing we know is we always need to pick a 0, right? And then the next one could be this one, this one, or this one. And obviously we need to pick this one is because it's further apart, right? And to be precise, the Hamming distance in this case is 2. And the Hamming distance in this case is 1. So in this case, the optimum 2-1 code is just 00 and 11. It's unique, right? So that's for the 2-1 code. And for the high-dimensional code, we can follow the similar argument, but the math is going to be a lot more complicated than this, right? In order to pick up the optimum code, but there are ways that we can do that. Right? Okay, but how to design those high-dimensional code is beyond the scope of this class, right? And a lot of the people that are actually working on the design of channel codes, a lot of them, they have math degree. Right? And generally speaking, engineering degree is not enough to do that. Okay. Any question? All right. Okay, so so that's just a visualization. So optimum decoder. So just now we talked about, in the previous section, we talked about the syndrome decoding, and I have been talking about the soft decoding, but I never mentioned how do we actually do soft decoding. So here I'm going to briefly introduce the concept of the optimal decoder, which is the optimal decoder. Okay, so if all the code words are equal probable, right, and which is the case in communication system. So all the code words, each code word corresponds to a length key sequence, and all those length key sequences are equal probable. If they are not equal probable, which means there is redundancy. And if there is redundancy, we can do compression first. After compression, they will be equal probable, right? And when we actually transmit the information, we always want them to be equal probable, which means there is no redundancy. We don't want to try and transmit redundant information, okay? So if all the code words are equal probable, and in that case, we can do maximum likelihood receiver, right? Based on what we learned in chapter 3, maximum likelihood receiver, if the information symbol is equal probable, maximum likelihood receiver will minimize the error probability, okay? So the optimal receiver here in this case is the maximum likelihood receiver. So let's develop the maximum likelihood receiver. So in chapter 3, if you recall, in chapter 3, what we talked about was y equals to x plus n. We are just talking about the transmission of one symbol. Okay? And our likelihood function is y divided by x. And our maximum likelihood receiver is just so S is the set of all the possible transmitted informations, right? For example, for MPSK modulation, this is the set of all the MPSK symbols, right? And we can write the likelihood function, and we would like to find the X that can maximize this likelihood function. That's what we discussed in chapters 3 and 4, baseband detection and bandpass detection, right? So that's the basic idea that we use. And also we use the vector representation. If these are vectors the same, we have the vectors, okay? We would like to maximize the likelihood function of the vectors, and where X is the vector representation of the modulated symbol, right? For MPSK modulation, the vector is essentially just a two-dimensional vector, the in-phase component and the quadrature component, right? So that's just a quick review of what we learned before. And similarly here, for channel coding, if we do channel coding, so our message vector, so let's see, the mth message vector, its length is k, okay? And here is a typo, it should be s. So all these are either ones or zeros, okay? And then we do encoding. So after encoding, this sm, length sm vector is mapped to a length n code word, okay? It's mapped to the length n code word. And once this length n code word, we can do modulation. We can do either BPSK modulation, or we can do more complicated modulation. And here I'm simply using a BPSK as an example. So the zeros are mapped to -1, and the ones are still mapped to 1. So we have X. Then we transmit the modulated symbol, right? In this case, our receiving information is X plus Z, where Z is AWGN. So that's R, okay? And our demodulation is we are trying to use R to figure out Y, okay? And we are trying to use R to do a we can use BPSK demodulation, we can use R to find Y. So basically, we do a BPSK demodulation. If R is greater than 0, we make a decision in favor of 1. If R is less than 0, we make a decision in favor of -1. So that's maximum likelihood detection, right? Once we have 1, -1, it's binary, and then we can do decoding, for example, by using the syndrome decoding, right? So that's the general way of doing that. However, if we do maximum likelihood decoding, we can directly use R to do the decoding. So what we can do is, the R obviously depends on XFM, and XM depends on CM, CM depends on SM. So for maximum likelihood decoding, we would like to find out Sm such that we can maximize R, the likelihood function of R conditional on Sm, right? Where Sm is our possible information vector, It's our length k information vector. So our search space in this case is 2 to the power of k, our subspace. Okay, the size of the subspace, which is also called, in mathematical term, is called the cardinality. Okay, the cardinality of a set, which is the number of elements in a set. Okay, just the fancy way of saying how many elements are in a set. Okay, so that's the cardinality equals to the power of k. Okay, so that's a finite set. The cardinality equals to exactly the number of elements in the set. Okay, for uncountable set, the cardinality definition is more complicated, but that's not relevant here. Okay, so that's the cardinality. So our search space is 2k. So basically, for each Sm, we can get a Cm. For each Cm, we can get an Xm. Once we know Xm, we can actually write the likelihood function. Okay, so for this particular case, PRSM equals to PRXM, right? And here is a typo. This Y should be R. Okay, this Y should be R. So that's before we do hard decoding. Okay, so PRXM, and because R equals to XM plus Z, so this is essentially R1, Rn, XM1, XMn. Right? So these are length n vectors. And because the noise are independent, so conditional X, the only randomness comes from Z. Right? Given X, the only randomness comes from Z. And for Z, each sample is independent. Okay, so therefore we can write it as PR, what is the index that I use here? Use N, okay, Rn, X, actually that's not using N because N is already, let's use U, okay, XU, XMU, U is from 1 to N. Right? Because they are independent, therefore we can write it as the product of each individual PDF. And what is PRU, XMU? And again, this is just a Gaussian, right? Sigma to sigma square, Ru minus XMU squared. If this is BPSK, right? If it's QPSK, it's going to be more complicated. So basically, we can write the likelihood function together, so which is the product. U is from 1 to N, 2 pi sigma, where sigma is the variance of AWGN, Ru minus XMU squared. And if we simplify this, it will be to the power of N, exp 2 sigma squared, U is from 1 to N, Ru minus XMU squared. Okay? And this term here is exactly R minus XM squared, which is the Euclidean distance squared between these two vectors. Okay, which is the Euclidean distance squared between these two vectors. And we have seen this notation in chapter 4 when we do vector representation.
A question?
Yes.
What is the 2 subscript?
The 2 subscript means that's a 2 norm. So the double straight line here means that's ai squared. I is from 1 to n. So the 2 subscript means that's a 2 norm. And we have different types of norms. So the 2 norm is defined as ai squared. And also there is 1 norm. That's 1 norm. And also we can define the p norm in general. Okay. So that's why I put a 2 subscript there. And usually 2 norm, actually we can skip these 2 subscript. If you do not see this subscript there, usually it means that's the 2 norm. Okay.
Okay, thank you.
Any other question? And as I said, we have actually seen this kind of notation in the previous chapter. So that's our likelihood function. And maximum likelihood decoding, in this case, maximize PR SM is equivalent to minimize the Euclidean distance. So now we are minimizing the Euclidean distance, okay? Of all the possible code words. Okay, we can try for 2 to we have 2 to the power of s, 2 to the power of k code words, right? For every single one of them, we can get an x of m and see which one has the shortest Euclidean distance with the received information. And that's our decoded code word. This is the optimum soft decoding. This is the optimum soft decoding. And the performance of the optimum soft decoding is actually much better than the syndrome decoding that we talked about in the previous section. But the complexity is much higher. As you can see here, we need to do an exhaustive search of all the 2 to the power of k possible code words. Okay? So in this case, instead of getting the 1s and the 0s before decoding, we directly use our received information R, which contains real information, to do decoding. So we preserve all the original information. And this is the optimal. This will give us the best possible decoding performance. All right? And again, it comes down to minimum Euclidean distance. We have seen the minimum Euclidean distance many, many times throughout this semester. So as you can see, the minimum Euclidean distance detection or decoding is a key theme in communication system design. All right? And the reason that we can measure Euclidean distance is actually because of the Gaussian PDF. The exponent of the Gaussian PDF happens to be the negative Euclidean distance. So maximize the Gaussian PDF is equivalent to minimize the Euclidean distance. That's why we can do that. Okay? Any question? So for this one, it will require exhaustive search. For example, for 5.3 code, k equals to 3, the number of exhaustive search that we need to do is just 8, which is fairly easy, right? And for 7.5 code, 2 to the power of 5 is 32, is still manageable, right? So when k is small, this is nothing, it's just a piece of cake, right? We can easily do the exhaustive search. But when k is large, for example, let's see if k is on the order of 100, then we can't do that anymore, right? If k is 10, we have 1024. If k is 20, it's about 1 million, right? If k is 30, it's 1 billion. So we can't do that anymore. So if k is even a few dozens, we can no longer use exhaustive search. So what we do is we utilize the special structure of the code, because the code word is not just any sequence. The sequence has to be in a subspace, and the subspace has some structure. The subspace is actually generated by using the generation matrix, right? So it has to satisfy this condition, and by utilizing this condition, we can develop some more advanced decoding mechanisms, okay? And that might sacrifice a little bit of optimality, but in general, the performance is also going to be pretty good, but with a much lower complexity compared to exhaustive search. Okay, one example for that is LDPC code, and for LDPC code, the K is usually on the order of a few thousands. Okay, so for example, if K equals to 2048, we can no longer do exhaustive search. Okay, no computer in the world can do that. So what it does, it's using the sparse structure of H. As I mentioned earlier, H needs to be a sparse matrix for LDPC code. It has just a few ones, most of them are zeros. It's using that structure to do an iterative decoding, and eventually it will converge. Okay, but that's something that is, again, beyond this class. Here I'm just introducing the general formula of the optimal decoding. Okay, and so this general decoding works fine when K is small, and when K is big, we can no longer use it, then we have to resort to some suboptimal mechanism, okay, by using the unique structure of the generation matrix G and the periodic matrix, check matrix H. Okay, so that's the optimal decoding. Any question? Okay, so that's the optimum soft decoding. Okay, the optimum soft decoding. And actually, we can also do the optimum hard decoding. Okay, we can also do optimum hard decoding. So this is optimum. So whatever I wrote here is for optimum soft decoding. And this will give us the best performance, okay? The best possible performance. And next, let's look at optimum hard decoding. So we introduced one possible way of hard decoding, which is syndrome decoding. But syndrome decoding is far from optimum. Okay? We can also do optimum hard decoding. So to do optimal hard decoding, the only difference is we have R, we do demodulation, we will get a Y. Y will be in -1 or Y, okay, to N. So we thresholding it first, okay, and we discard all the soft information. Instead, we have binary information, and instead we are maximizing the likelihood function here. Okay, so in the previous page, for the optimal soft decoding, we are maximizing the conditional PDF of R conditional X. And here for the optimal hard decoding, we are maximize the likelihood function of Y with respect to X. That's the difference. Okay? That's the difference. Any question? And the analysis here is actually easier. So let's see the optimal hard decoding. So again, so Y is from the demodulation of X, right? So again, we still have R equals to XM plus the noise, and then from R we do a decoding. So, and when we do decoding, that's exactly the same as what we did in chapter 3 for BPSK demodulation. Okay, so once we get Y, we could get the Y to be correct or the Y to be wrong, right? We can actually get the error probability, and we call it P. And for QPSK, this P is actually 2EB or not, right? And this EB is the energy per code bit. It's not the energy per information bit, right? So that's our P. So next we can use this information to find out this likelihood function. So keep in mind this y here are 1 or negative 1s. These xm here are also 1 and negative 1s. Okay? So again, py xm, and they are affected by independent noise. So again, we can write them as pyu xmu. U is from 1 to n. Okay? So what is pyu xmu? So if pyu xmu, we have actually two possibilities. If yu, keep in mind yu here could be 1, negative 1, and xmu here could be 1 or negative 1. If yu and xmu, they are the same, then which means we do not have an error. So there are two conditions. It could be either 1 minus p if yu equals to xmu, or p if yu does not equal to xmu. Okay, so keep in mind y now is a discrete random variable. It's no longer a continuous random variable. It's a discrete random variable. Okay, so error probability is defined as the probability that y does not equal to x, which is the Q function that we discussed in chapter 3. Okay, so that's P. And if y equals to x, which means we do not have an error, and the probability is 1 minus P. Any question? So that's our likelihood function. Okay, that's our likelihood function. And this is hard decoding. Keep in mind that's hard decoding. So y could only be 1 or negative 1, and x also could be 1 or negative 1. So in this case, py xm is the product of all these 1 minus p or p. Actually, we can write it as, so we assume that j bits are different. The Hamming distance between these two are j bits. Okay, we assume that the Hamming distance between y and x is j. Okay, so we have two binary vectors, and we can easily measure how many bits are differ between these two binary vectors. Let's see, it's j, then our likelihood function is going to be like this. Okay, any question?
So y is created by -1 and 1.
Where is minus 1, 1?
I mean, every element in y is either 1
Because
or
we
minus
do
1.
demodulation, or you can do 1 or 0. So we have the receiving
Because we
information.
had xm, every element of xm was 0 and 1.
XM is actually minus 1. It's simple. It's 1, negative 1. XM is 1 or negative 1. And then that's just BPSK modulation. So here it's exactly the same as chapter 3. We have BPSK modulation, we plus noise, we got R, right? And R could be, for example, 1.3 or 1.5 or negative 0.3. And then we do demodulation, we can get Y is negative 1 or 1, right? That's demodulation. Any other question? So that's our likelihood function. And we would like to pick, so actually it's better to write this as G sub m because it depends on our choice of the code word. Right? So we would like to find an m that can maximize the likelihood function. Okay, we want to maximize the likelihood function. And if you look at this expression, it might not be obvious about how to pick the m to maximize the likelihood function. So on the other hand, if we write it in the log domain, okay, I'm going to write it in the log domain. So that's our likelihood function. And maximize the likelihood function is equivalent to maximize the log likelihood function, because log is a monotonically increasing function. And that's a trick that we commonly use, right? And that's the same thing that we did for the soft decoding. We maximize the log likelihood, right? If we take the log, it's going to be Jm log of p plus n minus Jm log of 1 minus p. Okay? So the only thing that is changing is Jm. So I would like to put Jm together. Okay, so it's just a simple change of order. I group the two terms with Jm together. And why does this help? So maximize. So the only thing that depends on m is this Jm here, right? So maximize the log likelihood ratio is equivalent to maximize Jm log p minus 1 over p. And the second term is a constant. It's independent of our choice of m. Okay? You can put the second term there, it's not going to affect anything, right? It's equivalent to choose the m to maximize this thing. So how do we maximize this thing? Let's think about p and y minus p. Is p greater than minus p or less than y minus p? So is this thing, the factor here, the fraction here, greater than 1 or less than 1? Think about it. Should it be greater than 1 or less than 1? So what's the meaning of p? P is the error probability. And for binary detection, our error probability can never exceed 0.5. If the error probability is, when the error probability is 0.5, which means we don't do anything in our detection. We just randomly guess, right? We have a sequence of 1 and zeros. You just randomly guess. This is 1, that is 0. You don't look at any information. You will get a 0.5 error probability, right? Random guess will give you 0.5. And if you do any kind of detection, it will give you error probability less than 0.5. So p is less than 0.5. So this is less than 0.5. 1 minus p is always greater than 0.5. So this thing is always less than 1. Okay? Because for error probability is always less than 0.5. Okay? And if you design a decoder that has a performance that is worse than 0.5, you can just throw away your decoder. You just do random guess. It will do better than that. Okay? Random guess will give us 0.5. So which means log of p or 1 minus p is less than 0. Okay? So this is a negative number. So maximize a negative number is equivalent to minimize a positive number. Okay? So for example, if log of p or 1 minus p is negative 2, so maximize minus 2j is equivalent to minimize just j. Okay? And what is j? J is the Hamming distance between y and xm. So the optimum hard decoding, not surprising in the end, it tells us we need to minimize the Hamming distance. So basically you receive a code word, it's corrupted by noise, and then you do demodulation, you got a binary sequence, okay, Y, and then you just compare the Hamming distance between Y and the transmitted code word, all the possible code words, and see which one has the smallest Hamming distance. Okay, so in this case, the optimum hard decoding is just to minimize the Hamming distance between the received information and the 2K code words. And in this case, the complexity is similar. Still, we need to do a search over a space of 2 to the power of K. Okay? The only thing that is easier is we don't need to do y minus x squared. We just compare these two bits the same or not. So real number operation is simplified into binary number operation. So in computer, binary number operation is much, much faster compared to the floating point real number operation. Okay, so which means it's faster, the complexity is lower, but we are sacrificing the performance. So it's a trade-off between performance and complexity, between hard decoding and soft decoding. But in the end, they all boils down to the comparison of the distance. For soft decoding, as we just saw, we want to minimize the Euclidean distance between the received information and the code word. And for hard decoding, we want to minimize the Hamming distance between the received information and the possible code word. Okay, so that's our optimum decoding. Any question?
I have a question. So it's not clear to me why the optimal soft decoding gives the best performance compared to the Hamming, the hard decoding. I mean,
so your question is, why is maximum likelihood the optimum one?
I mean, why the soft decoding gives the best performance?
The soft decoding, because we are using, for hard decoding, we have thrown away. So the more information that we use, the better performance that we will get, right? And during the detection process. For hard decoding, we are hard decode, detecting all the real information into just the two binary values. It's like quantization, right? We are throwing away useful information. So by throwing away useful information, our performance has to suffer. Okay? So that's why the hard decoding is worse than soft decoding. And for soft decoding, we are just simply using maximum likelihood. So we can prove that you can minimize the error probability, as we discussed in chapter 3. Okay? So soft decoding has the best performance. And if you throw away some additional information, you get hard decoding, which is still pretty good, but the performance is not as good as soft decoding. Okay? Any other question? All right, so we spent a lot of time here actually talking about the optimum soft decoding and our optimum hard decoding, just to give you some idea about the difference between soft decoding and hard decoding. And in the end, at the end of the day, you can see what we do is just to compare distance. It's either the Hamming distance or the Euclidean distance. Okay? So that's our optimum decoder. So since P is less than 1 minus P, so I have exactly what I wrote there. So the optimum decoding is just to minimize the Hamming distance here. Okay? So that's the hard decoding. And that's a visualization of a 6-tube space. So every single circle here is a possible 2 to the power of 6 sequence. Okay? And how many circles we have? We have the code word length is n equals to 6. 2 to the power of 6 is 64. Okay, it's 64. So totally, if you count, we will have 64 circles here. And these big black dots are our valid code words. Okay, and how many of them that we have here? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8, so which means our k equals to 3. So that's a 6-3 code. That's a 6-3 code. Okay, so these are our code word. And for this particular code, it's, and actually around each of the code word we have a sphere. And so on this sphere, it means all the code word, all the sequence that has Hamming distance 1 with the code word. Okay, and how many do we have here? Because totally we have 6 bits, so we will have a total of 6 possibilities. If you flip 1 bit, it will get here, right? Flip the first bit, flip the second bit, flip the third bit. So totally we have 6 sequences that has a Hamming distance 1 with a desired code word. Okay, so 101110 is our code word. If you flip 1 bit, you will get here. Okay, and all these sequences on the inner sphere has a Hamming distance 1 with the desired code word. And for the outer sphere, they have a Hamming distance of 2 with this desired code word. Okay, so this is a sphere. And also we can see there is no overlapping among the spheres. Okay, which means the Hamming distance in this case is at least 4. Right? If the Hamming distance between 2 code words, the minimum Hamming distance between the 2 code words is 3, and then these 2 spheres will overlap with each other. Right? And if their Hamming distance is at least 4, then these 2 code words, spheres, they will not overlap with each other. Okay? So, and again, this is a visualization of the space. This is a 6-dimensional space. We can't, draw exactly the 6-dimensional space as what I did for the 2-dimension, but you got the idea. So in the 6-dimensional space, you can imagine we have lots of high-dimensional balls, right? And these balls, they do not overlap with each other. And on the surface of the ball, it has the sequence that has a Hamming distance 2 with the center of the ball. Okay? And these balls, they don't overlap with each other. And in that case, we have a minimum Hamming distance of 4. Okay? A minimum Hamming distance of 4, which means we can detect 3 bits of error and correct 2 bits of error. Okay? So because if we have 2 bits of error, and it will have to fall in on one of the points in the ball. Okay? If it belongs to this ball, and then we can make a decision in favor of the center of the ball. Right? If we have 3 bits of error, so let's say if we transmit this sequence, and 3 bits of error will make it to be on the ball of its neighbor. And when we make a decision, we will make a decision of its neighbor's center. So we are going to make an error. Okay? So that's a visualization of the correction and detection capability of the linear block code. Any question? All right. So that's a visualization of the 6 tuple space. And next, let's look at the error performance. Okay. So message error probability. So the probability that the decoder commits an erroneous decoding. So the probability that there are more than t bit of errors. Right? So let's see, the error correction capability of the code is t. And if there are less than t bits of error, or equal to t bits of error, then our code can correct it. We are fine. Okay, so we are not going to make any mistake. If there are more than t bits of error, then our code will no longer be able to correct it. All right. So which means the message error probability, which is the probability that our linear block code can no longer recover the original information, is exactly the probability that there are more than t bits of error. Okay. So if we consider simply BPSK, 1 bit of the probability that any 1 bit in error is p, right? For BPSK, p equals to 2EB or not, as we learned in chapter 3, right? So the probability that if we have a length n sequence, and the probability that j bits are in error is this one, right? J bits are in error, and the remaining n minus j bits are correct. Okay, so that's the probability that the j bits are in error, and the remaining n minus j bits are correct. In the meantime, we need to consider n choose j, because it could be, for example, if n equals to 5 and j equals to 2, we could have the first 2 bits in error, and the probability that this sequence will happen is, so this is our error vector, right? So the probability of this error vector is p squared 1 minus p cubed. we could also have the error vector look like this. And again, its probability of this error sequence to happen is p squared 1 minus p cubed. And totally, we have 5 choose 2 possibilities, right? 5 choose 2 possibilities. So that's why we need to add them all together, okay? N choose j possibilities, j bits are in error, and the remaining n minus j bits are correct, okay? So we need to make sure that this is actually not to infinity, to n, right? If we have more than t bits are in error, if we have more than t bits are in error, then our message will be in error. And this summation here is actually because there are some events that overlap. It's not an exact relationship. It's an upper bound. Okay, it's an upper bound. So our message error probability is upper bounded by this expression here. Okay, that's how we get this expression. Any question? Okay. So the bit error probability, so we got the message error probability is the probability that the decoder erroneously decode a code word, and the bit error probability can be written this way. So here in this case, it corresponds to j bits are in error, right? J bits are in error, and totally we have n bits. Okay, so that's the bit error probability. And again, it's not an exact relationship; it's just an approximation. That's a fairly accurate approximation, I would say. Okay, so that's the bit error probability. Any question? Okay, so just a quick example. So let's consider a 16.8 linear block code capable of double error correction. Assume BPSK is used with the received EB over naught being 10 dB. So what is the message error probability? What is the bit error probability? Okay, so for this one, we are considering n equals to 16 and k equals to 8, right? N equals to 16, k equals to 8. So in this case, and our error correction capability is 2. Correct 2 bits of error, double error correction, okay? And the first, our Q is 2 EB over N naught, and our EB over naught is 10 dB. 10 dB is actually the linear value of 10, okay? 10 dB equals to linear 10. So that's 20, and you can use the Q table to find the number there. And the message error probability will be less than or equal to J from 3 to 16, 16J, PJ, 1 minus P, 16 minus J. And this is fairly tedious to calculate, and actually this equals to J from 0 to 2, 16J, PJ, 1 minus P, 16 minus J. Okay? So we can calculate the inverse. Okay? This is the probability that we have 0 bits, 1 bit, or 2 bits of errors, right? And for all these we can correct, then the remaining probability is just 1 minus that. So for this one, it's much easier to calculate. You can just type it into your calculator, okay? And our bit error probability will be 1 over 16, and based on our expression, J is from T plus 1 to N, J 16 to J, PJ 1 minus P, 16 minus J. Okay? And for this one, it's not that, I mean, we can still simplify it, but it's not that straightforward. So for this case, it's better just to write a MATLAB code to calculate it, right? Any question? All right, so that's just an example about the error probability here. So in today's class, we spend most of our time talking about soft decoding and half decoding. So just to give you an idea about the optimal Okay? All right, so I'm going to stop here today, and we will continue on Thursday.